So again, like I said, thanks, Chris. Introduction into CODESYS SoftMotion is what we'll begin with today. And really what I'm going to kind of give a quick agenda of what I'll be talking about this morning. I'm going to first begin with just an introduction overview, just kind of a general overview, and talk a little bit about, really where motion is and where it came from, how we got to where we're at, and then a little bit of discussion about PLCopen, mainly the motion basic standards and specifications. I'll go through CODESYS SoftMotion basics and FBs, and then I'll be going through the CODESYS SoftMotion drives and interfaces, followed by SoftMotion, and then resources examples, and we'll do the overview of the software, and then I'll conclude. And in my conclusion, I'll be showing you just a quick demo, some function blocks inside the ladder logic diagram, and put some blocks out there, show you how they work, show you how to start up a real basic motion control system. So the introduction and overview. So looking back at the motivation of the motion control inside the PLC, I'm going to kind of step back about 25 or 30 years ago. There's really two separate devices, the logic controller and the motion controller. And those were separate communications. So ultimately, all of those devices, or when you had those devices, specifically the PLC, the motion control, you're going to have the synchronization, the comms. All of it were very difficult to set up, and a lot of times you'd have probably some sort of engineering tool set in which you would do the PLC, you'd write the code, and then you'd probably do your motion control, and then you'd be sending signals back and forth, and then not only that, you'd probably be parameterizing each one of the drives. So by the time you got done, you had a communication cable, a whole bunch of I/O strung back and forth. You had your probably 3 or 4 different types of programs, and it just, it wasn't very efficient. And there were several different types of engineering tools, and to have to sit there and maintain all that got very difficult. And then knowing which one to use when, and it was very expensive, and it was very cumbersome back then. So things began to change. What happened is we kind of went to one device, but there's still different tools. So in the diagram here, I'm kind of showing that basically you have your control, your software, and your motion controller together, but you're still running your configuration software and possibly maybe even your scaling, as far as like how you're going to scale your parameters, how you're going to scale your actual kinematics of your device. So, it's almost there, but not quite fulfilled yet. And synchronization and communication was still not as easy. Again, you were probably having to go into this motion control configure the software, make it talk back and forth, set up the basically maybe data links, data blocks, whatever you're doing. Maybe it's straight up analog, but depending on the actual motion control itself, be dependent upon that. So we stepped through today, and today we basically have one device, one tool. And in the case of CODESYS, we're using motion, CNC, and robotics all in one. So now you use one tool, less complicated. Everything is housed within the IDE. The synchronization, communication, both systems are all in one process. So you're not separating out 2 different pieces. The PLC, logic, the motion applications are actually all in one project now. So you're not configuring your PLC on one aspect, then turn around and configuring your motion control on another. You're putting them both into one, basically the CODESYS IDE. CODESYS motion control, the big points I want to push out there are basically, we're doing point-to-point, we're doing gearing and camming, and then the added part would be the CNC and robotics. So today we're kind of filling the full gamut of things at which we can basically work with and do. And that was kind of the that was the goal from the get-go. And again, this, to be clear, all of this was designed probably about 2011, I'm thinking, somewhere around there is when we really put in the CNC robotics, but the actual base points here of point-to-point gearing and camming, that was actually before that. So that would have probably been like 20 years ago. So much like I said, I wanted to talk a little bit about PLCopen and the basic standards and specifications. So looking at PLCopen, if you're not familiar with it, PLCopen is basically there for enhancing the efficiency. And I put up here automation through open standards. So really PLCopen it's comprised of members of typical suppliers, right? Users, machine builders, applications, specific developers, people that basically know their industry, know their applications, basically know their trade, or I should say their discipline. And the PLCopen, if you're not aware of it, first of all, is headquartered in the Netherlands. Offices are in the US, Japan, it says here China and Korea. The main focus for PLCopen, the reason it was created was to create like a technical specification. So this is where you hear about the IEC 61131-3 standard. And the real fundamental reason was, was to not only reduce the cost of industrial engineering, like probably, the time to get your product to market or so forth, but it was really just to create like a standard. So we're not having all these vendors do specifically different things along the way, meaning that, vendor A is kind of rates blocks and stuff one way, vendor B does it a different way. It was to kind of create a standardization throughout the industry to simplify it for industrial engineers or automation engineers. The important outcome, like I said, was really the standard libraries. The standard libraries, basically for different applications, different fields, excuse me, basically harmonize the language, conformity, and levels. Really the engineering interfaces for the exchange between information, transparent communication, and really just overall, the concept was to increase the software quality and decrease software maintenance and uptime cost. A lot of times software in today's world has like a very large maintenance cost or something like that. And the idea was to make this an open source at that point. So the development and concepts and definitions of the open standard was really created by technical committees made up from, like it says, experts from many PLC of the open members are technical experts. And the idea is that giving expert information in regards to how this should, the block should be built or how it should go, is really standardizing the industry and making it more functional for engineers. And it's easier to work with a function block when somebody is very specifically knows how your function block is developed, how your industry or your discipline works, whether it's maybe, let's say, a rewinder, or it's maybe a packaging machine or something along that line. The library developments included FB developments for motion, safety, OPC, UA, etc. So this really scales up. Basically, the specifications for PLCopen was to go across the entire spectrum. And again, like it says here, talking about logic, motion, safety, it was really to cover the span of different disciplines or controls. So for further details, I really do recommend, if you get a chance, go over to www.plcopen.org. It'll give you a very nice idea of what PLCopen is all about, specifications, standards, guidelines. So it's very valuable if you get a chance to go there and take a look. So for the motion control standards in PLCopen, I'm really going to concentrate mainly on the first two parts. The first two parts is really the motion control guidelines. And this was released again about 25 years ago. And if you can imagine back then, it was probably doing a lot of just a simple pick and place movements, velocity, and some of that stuff. And later on in the extension that came out, that was around 2011, it came out, and that was a release to kind of merge in some of the things maybe they missed in the first part. And what that would probably entailed and would be maybe if they put in any sort of specific ways in which the blocks would function, the function blocks for the standardization. And I'll be talking further about when I refer to standardization, what I'm really getting to. And kind of just to give you a quick piece of what I'm referring to is like maybe like the enable, the execute, the done bit that we see in motion, the busy, the active. Those are all comprised of basically a standard that was created within PLCopen. So the guidelines, like I said, really referred to coming in part 2, 2011. And then there's actually several parts to this, part 3, 4, 5, and 6. And part 3 was really more or less when it got released from PLCopen, how to use the function blocks and use cases. And if you've ever gone into the PLCopen, into their website, what they'll actually show is like a sample of it. Could be a flying shear, could be pick and place, could be a roll handling system, or just mainly a rewinder, a little web system, maybe registration. So it's actually really good to go there and just take a peek, see the blocks, and they actually have blocks that pertain to what you would see within CODESYS. Later on, part 4 came out, which was really the robotics and CNC part of it. And then to follow was the homing procedures, and part 5 of the published paper. And again, these are all published, I would say, papers for the most part. Homing procedures. When we talk about homing procedures, it's generally configured on the hardware, not programmed. You are able to do that inside CODESYS. There is the blocks for homing, but there's also just what they call the, I think it's the SM homing block, and that's really, or MC homing block, and that's really just for you hit it and it zeroes it out. But you can actually configure if you want to go to, let's say, a specific hard stop, or you went to a proximity, you hit it and you came back off of it. How much do you want to come off? Those kinds of things, just really the homing process. And again, like I said, those are generally configured on each hardware because most hardware has its own way in which it wants to be homed. For the fluid power extension, that was part 6 of the PLC part of it, PLCopen motion control. And those are really special needs for with inside fluid power applications. When each one of these parts are looked at, basically each specification contains 3 sections. And they really try to quantify down that the definition of the state of the machine. So you have like what they call the state machine, which I'll be showing you. But more so is also the definition of the basic function blocks for a single or multi-axis motion control. How are those going to work? What should they look like? Everything is, each piece is kind of taken into context to look at each individual bit or status bit or presentable parameter within it to understand how it will work. And then ultimately the compliance and rules and certification procedures. So they really do a very thorough job in going through it. And like I had mentioned here, if you get a chance, I really advise you jump to www.plcopen.org. I think every time I went there, I've seen something different. I've learned a little bit. I read through the spec or the guideline, and said, hey, what a great idea. So it's really get a chance again, please check it out. So the ultimate, I think this is my final slide here on this, is the PLCopen standardization. What does it mean for basically an end user, an OEM, machine builder? Well, the idea was for users to wish to be able to port their application from one type of software device to another, from one controller to another, very few issues. And that's really the common goal, is consistency. Consistency in the function block and the behavior of the function blocks, how it's going to handle, how it's going to work within each other, how they interact with one another. So to say that it was 100% portability between vendor, a little bit tough, I would say, to say that at this time, because each vendor is going to have their own specific maybe function block. It'll generally the main parts will be in there, but could be a little different because of maybe the way in which they might have a special function within their device, right, that turns on a specific way. But for the most part, and I put in here that in my opinion, it was a major achievement, a huge success, because motion control is a standard. Trying to quantify that down and make it as one piece was really a great fit for the industry, right? Engineers, the idea was, again, for engineers to know a standard and have experienced in one vendor's platform and then be able to transfer to another one and know the similar behavior, how that block's going to work or how that specific function will work. So the decision for motion control blocks to be applicable in 61131-3 languages. There's some factors and considerations, and I wanted to just cover this because I think it's important to understand how this is viewed. Basically, it's objectives, simplicity, right? The efficiency, how efficient they can be, consistency, universality, flexibility, and completeness. So that's really the goals behind each one of the motion control function blocks when each one gets kind of audited, is what I would say, or looked at. Now what I'm going to do is I'm going to jump in and talk a little bit about the basic concept of the function block commanding and just an overall behavior. I put and behavior model. So how does this work? So I'm not sure. Are you able to see my mouse on here right now, or yes, no?
Yes.
Okay, thank you. So what you're seeing here is basically, this is a function block. This is an MC move absolute block. And if you notice, this is an execute block, and meaning that there's the axes and then the execute. Down below, this is a completely different, not completely different block, but a different block. It's axes and enabled. So I'm going to talk about the first block, and then I'll go and talk about the second block. So on the first block, the thing to notice is that really the two different behavior models of these two different blocks, and again, these are standard between every type of this type of block, meaning like if it's a read actual torque, read actual position, read actual velocity, or if you had a move absolute, move relative, is that you're going to have the axes, the execute, you're going to probably have your position, velocity, you're going to have the consistency of what you would expect inside of a motion control system. You're going to require velocity, acceleration, deacceleration, jerk, possibly your direction. But really in this block, what we're focusing on is overall is the, excuse me, the execute block or the execute input, and then the done, busy, active, and abort. So I'm going to take a look at this over on the right side here, which is the FB1, FB2, and FB3. So you can see by this diagram that basically the first execute happens. And when this execute happens, it says it's active. So this block will execute and say, you'll see a done bit that'll say, or not a done bit, but an active bit that'll turn on. Then once it starts to go, it's actually in the process. Excuse me here. It's actually in the commands waiting to be moved. It's going to be running. It's going to give you this first done bit when it's complete. And then the second one will turn on. So at each point of these function blocks, you know if it's active, if it's done, or if it's busy. So once you execute it, it's going to give you basically the active and busy. So it's already in the point, you know that that block is running. When the block is completed or executed and finished, you get the done bit. In this case, they're firing FB1, comes over, it gets the done bit, which executes FB2, the second block. The second block is executed, turns on, it says it's active, and then when it's finished, it's done, it sends the done bit. Goes high, and it shuts off. The difference on the third block is that this one is actually being ANDed. So it's looking for input 13. I'll say input 13, this is in 13. Input 13 and the done bit both have to be basically ANDed. And then what will happen is they'll turn the execute on. So you can see down in the actual diagram that when it tries to execute, it's being executed because input 13's on, turns on, it's executed. The done bit's already done right here on the second one, second function block. So right in this area, you can tell that input 13, we're both high. So then the execute will turn on. We know we're active, but if you notice down here at the bottom, this block did not get done. And the reason the block did not get done is because when it went to turn on, actually seen that there was an error that occurred somewhere during the block. So what happened is the done signal never came on. So this done bit would never turn on. Therefore, the block would never say it's finished. I think the key thing to note here is that there's actually these bits, these execute, done, busy, and command aborted, for instance. All of these will be showing up in throughout the blocks as we talk about them. But if a block is running and another block turns on, what'll happen is that block will be aborted. Okay, and I'll be showing that in my demonstration. So let's look at the enabled block down here, this read actual torque block. And really within this block, what happens is you're going to give it the axis name, and then you're going to enable it. And what'll happen is you'll see that it's busy. If you have an error ID, and here it's going to give you the torque. It's actually going to tell you the actual torque will be read out of the block, and it'll tell you if it's valid. So these are more, if you've seen here, this is more of a defined as a level triggered versus on these specific blocks are more of like, basically it's on the rising edge. So it's edge triggered. So when you take these blocks, this first block, and you pulse it on, if you were to pulse it on, it starts immediately. And if you pulse it off, it continues to stay on. For instance, in this MC move absolute. With this read actual torque, you turn it on, it looks for a level. If it's on, it's reading. If it's off, it's not reading. Okay. So now I'm going to talk a little bit about the state machine and the axes ref state machine specifically. So looking at this specifically, you can see that every axis follows the state machine, and that really there's this is inside PLCopen, this is documented, this is how it should go. And so this is kind of a standardization, knowing when the transitions, explaining when the blocks should be executed. So that's really the goal behind the state machine, is to be able to see that, for instance, if you're disabled, you can only go into a standstill mode, and you can execute the standstill mode. And then from the standstill mode, you can either go into stopping or you can go into homing. So there's a very specific way in which the state machine will function. And in this case, if you go into a standstill mode, the only way to come out of it is you can go back and say you're done and go back to a standstill, or in which case you would execute, the homing would be done, and it would say, let's go into a stop mode. So in the stopping mode, when you're actually stopped, you generally are going to spend most of your time, I would say, within the discrete motion, the synchronized motion, or the continuous motion. And it kind of gives you a listing of the blocks underneath discrete, the synchronized motion, or the continuous motion. Inside continuous motion, you're going to see that you have the velocity, the profiles, you're going to have your torque control. Inside synchronized, that's going to directly relate to your camming and gearing, basically any way in which you combine axes. Discrete motion is going to be moving and superimposed. Really, this is like your moves, like your simple pick and place, your move to absolute, relative, additive, and so forth. The idea, again, behind the state machine is to know which state or which block is being executed, how you entered that block, and how you executed it, and how you came out of that block. Again, in this example, we showed simply how you disabled. You go to standstill. You could either go to stopping, maybe you go back to standstill, you go to homing. So this is just to give you an idea of the actual state machine, how the function blocks execute, in which order. This has been very valuable, not only here, but also regards to PAC-ML, if you're familiar with that at all. So it's very, very nice to be able to see this and be able to understand what state the machine's in, and be able, when you're programming, to jump into a state, come out of a state, and know which one you're in. So now I'm going to talk a little bit about the blocks in general. As I get inside the code towards the end of the actual presentation, you're going to be able to see that I have the SM3 basic administrative configuration, SM3 basic diagnostics, and there's actually folders. And these folders will break out your function blocks based on what they're supposed to do, right? So movement folder is going to contain, like, obviously your movements, your relative, your absolutes, where inside like a master slave folder, that's probably going to have something related to two axes working together. So it could be camming or gearing or something along that line. In this specific one, I'm going to show you just in this example, in the SM3 basic administrative and configuration, you're going to see that this is really where you do the power. So you have to turn the drive on, you have to power the drive on. The MC reset is when you'd want to reset specifically an error. Let's say if you had a start, you tried to start something, and if you tried to stop something and you didn't have a deacceleration in it, or had a jerk maybe inside that stop block, if it was at 0, it's gonna register and say we have an axis error, invalid, accel, decel. You would see that show up. So this is where you would want to do a reset at that time. The MC set position, obviously you can see over here, you're setting a position. So these 3 blocks are kind of administrative blocks. And by no means is this the only blocks within that folder. I mean, you'll see when I open it up, there's a lot of different blocks for you to pick from for the administration part of the basic motion. But again, each one of them, see the consistency is you have an axes, you have an execute. In this case, you have an enable, and you have basically a status of some point telling you that in this case is the regulator on, is the drive start on, is it done, is it busy, is it aired. So that's really the idea behind the administrative blocks, is it's kind of monitoring the axes, kind of giving the instructions on or off, and setting specific things within that axes. In the next set of blocks, it's called the basic diagnostics FBs. And these are generally giving you the read actual position, the torque, the velocity. It's giving you status on the specific, basically the motion, the axes that you're referring to. So in this case, you can see again, we have the axes, we have the enable for each one of these. So these are going to be kind of that level triggered, right? It's not specifically like a rising edge. It's just you turn it on or off and you can be able to see your axes of motion, the real action, excuse me, the read actual motion, torque or velocity. There's also blocks to see if the read axes error or the MC read status. MC in position. Are you in position? What position? What's the window? And this read status block specifically is really nice because it tells you, are you stopping? Are you starting? Are you standstill? The type of motion you're running, discrete, continuous, or synchronized, constant velocity. Are you possibly homing? So this block is very important. I feel that it really gives you a sense of that axis of where it's at, reading the status of that specific axis. The next one is really the MC3 basic movement function blocks. And obviously you can tell by the movement folder that we'll be looking through is it's going to give you the halt, the home, the jog, the absolute, relative, velocity, and stop. So each one of these, if you can tell, is related to essentially moving the axes, right? So on the halt, for instance, if you were to halt an axis, you are literally halting it. If you give it, in that case, you're stopping, you're decelling to a specific speed. Even if you have this block on, you can override that block, for instance, with a move. So even though this block was told to halt, you can send a move command and it will actually override the block. Whereas the stop block, if you tell something to stop, it stops. It does not move again. You have to turn that block off. So this block right here, the stop block, if it's on, you cannot move. Where if the MC halt block was turned on, you can actually make the move. Again, the language being try to be clear is that it's MC halt, you're halting it versus a stop. The home is strictly that. The MC home, when you fire this block, essentially you're going to tell the axes to home, and generally it's going to give a position at that time. So if you say axes ABC, you execute this block, whatever's in the position at that time is what you're going to execute as the new position at the time. Okay, so that's when you're actually homing at that time. Again, the homing to me is a little difficult because each product that people maybe use for a servo drive or stepper or whatever you use could be a little different. They probably have very specific in the way in which they want their device homed. So a lot of times you may just be signaling a home or doing something along, which is compatible with that device, not necessarily using our larger home that we have built for a function block. Jogging, obviously going forward and backwards, you can understand this block as you're running, you can go in one direction, it'll decel down, and you just reverse jog, it'll go back the other way. Again, you're setting up the axes and you're giving all the information for the block, acceleration, velocity, jerk. And out of each one, you're getting the busy, tells you if commands been aborted, such as while it was running, did something else happen? Errors or error IDs. Relative, simply relative. So if you're at a specific position, you're going to move off of this position at a certain amount. A lot of times this is referred to possibly as an incremental move versus or a relative move versus an absolute move. When you tell it to go to 10 inches, your motion control, you're specifically saying go to 10 inches. And then from there, what will happen is if you say go 10 inches again, it doesn't increment up 10 inches. It literally stays there. It will not move because you're already at 10 inches. And then the move velocity, very commonly used for basically you're going to control the velocity or speed of maybe your servo drive. And again, just because you use the move absolute or relative does not mean you have to use absolute and velocity, because the drive wouldn't move. Obviously, in here you're setting the velocity inside this move absolute, or you're setting the speed inside the relative or the jog. So this is just to basically make the axes move continuous in one direction, almost like as forming like a VFD, I guess, if that makes sense. Then we move into SM3 basic master and slave. And what this is really referring to is like a master follower, master slave. This is in regards to now you're actually combining two axes together. So you probably have a master and a follower, and it's going to run, or slave in this case. And what happens is you can gear in and out. So I could have, for instance, I could have axis 1 running, and that's the master, and it runs at a specific velocity. And maybe I want to gear in the second axis. And once I gear in, I can specify in here the ratio at which I want to gear in at. So it could be 10-to-1, 2-to-1, 10-to-1, whatever you need basically for your gear reduction. The gear in position specifically, the gear in position like basically couples the slave to the master axis, taking into the account the specific position relationship of where it's at. So basically it's synchronizing the slave at precisely with the master at a specific time. So once you lock those two geared in position, they're continuously at the same 1-to-1. Okay. And again, in that specific instance, you can specify the actual syncing position for the slave or the master, and again, the ratio. Notice throughout these blocks, we continuously see, we talk about the word that it's going to have like a master axis or slave or follower axis, the execute, and your ratios. At any given time that you wish to decouple the slave from the master, you would give it an MC gear out, and that'll decouple it. Generally, I would say for the most part, if you're going to decouple something, you're probably going to want to bring it, slow it down, stop it, or when you do decouple it, maybe stop it at that time. The next part of the blocks, not only with gearing, which is very common, is camming. And camming is one of those things where you have a cam profile possibly currently in your machine today, and it has a specific profile, and we'll be looking at that. And you basically call up the cam table, and you execute the cam table, you cam the drive in, and here you would cam in the master will be running, the slave will be cammed into the master or the follower, and then the MC, when you don't want to cam it anymore, you can cam out. That means you basically uncouple the slave or the follower device from the master device. And there's another block called phasing. Phasing is really a phase shift. So if you were running something and you decided to shift it off a little bit, let's say you had a 1-to-1 ratio, we'll use that, and everything was running continuous at the same speed, and you needed maybe the slave axis to be, or the follower axis to be off by 20 degrees, or a specific position, not 20 degrees, but a specific angle from the master, then you could actually say, I need you to be off by 20 counts or whatever, and it'll actually move ahead 20 counts. It'll continue to do a 1-to-1 ratio, but it will be a little bit ahead of the other one. So it's very good. Again, it's called the phasing block. Very specific to your application. And again, it's a very good block. So out of this, the basic master and slave, I put cam, gearing, and cam tables and phasing. Those are the blocks. And consistently, as you go through the blocks, you'll notice it talks about master scaling, slave scaling, or if not, numerator and denominator. And each one of the blocks is very consistently laid out. So I was talking before about camming, or just a little bit ago. And the thing I wanted to show is that we have a very nice graphical user interface for this, that in which you can actually drag these points. So you can see here, I have these little points on here, and you're able to drag them up and down. And as you're changing this, or you're changing possibly the velocity or the slave acceleration or jerk, you actually see your profile begin to change. And this is really your profile right here. So how this works is that in the X column, we're going to say this is our master axis. So our master axis, when it's at 0, we're at 0. When our master axis is at 120, we're going to be 360 degrees. So that means once it's coupled in, once you send this cam table right here, this cam table right here down into the controller, and you say cam in, at that time, once you start, you do a velocity, let's say start, and you're doing a rotary, a modulo rotary. You're spinning it in a circle. Let's say your drives, you'll see that they'll stay locked on. And as you start the first one, as the master gets to 120 degrees, you're going to see that your follower is going to be, or your slave will be at 360 degrees. That means it'll actually do a full 360 degrees. Then at 240 for your master, your slave would be at 170. So this is really, the way I describe this is X is going to be the primary, Y will be the secondary. So kind of think of it as the X is the master and the Y is the slave or follower. Okay, and you can see here that without getting too far into it, there's the cam table. So if you click right here on the specific basically if you split a folder, I should say, but tab, you're actually going to get this cam table. This is the way it looks, and you can lay it all out. And if you've never done this, I would say I advise you to just put one in once and try it and see it. And it's neat to try it because it's really taking gearing and camming is such a large part of the world with packaging machines and different things that really, I would say a majority of the applications out there are probably running some form of gearing or camming in it. So, all right, this is in regards to talking a little bit more about interfaces. This is the CODESYS SoftMotion drive commissioning interface. And this specific interface is really, I think, important for a lot of aspects of what I do. If you were to call in and say I had an issue and this is what you're struggling with, and if you had an axis sitting there, chances are I'm going to push you right into this commissioning interface right away. The reason I would is because that'll allow us to get some control over that drive and understand what's going on. And again, we don't make hardware, right? So we're helping you look through it or design it. Now, the beauty of this commissioning tool, I feel, is that you can have your programmer, let's say you have two people there, kind of the experienced technicians working on the machine, working with kinematics, working through it. Maybe they're working with a mechanical engineer. They can go out to the machine, they can boot up this drive commissioning interface, get stuff working right away, and they can actually start testing the actual mechanical stuff. So as a controls engineer, I always feel like they're always waiting on me, right? Mechanical people are always waiting on me because once they get done, it seems like I have a little bit of time to get stuff done. So this can kind of get them going, get things moving. And in the meantime, I can step off to the side and write my code. So that's why this, I think, is such an important commissioning tool. And again, I'll show you today how this works. But what I want you to take away from this screen is that we have the power, the error reset, the homing. We have kind of the FBs. It tells us as we're running stuff, it'll tell us, are we in a standstill stage? Are we in a moving stage, a power on stage? And plus we can look actually at the parameters, and we can pick out a specific parameter and go look at it. And then we can see, in this case, parameter 113, and I tried to make a diagram down here at the bottom, copy and paste, hopefully you can see it, is, the maximum velocity software limit. And that is this right here in my dynamic limits. So this is set to 11, it's set to 100.11. And you can see here, it says down parameter number 1113. I go and look at that parameter and it gives me exactly 100.11. So it allows you to look at parameter sets and see where they're at. Is this super important? It can be valuable, but I think really the proof is in when you start jogging this thing around, you're gonna actually see it moving, okay? Drive support. I think this is an important screen. We talk about this a little bit as far as the drives of numerous servo drives available that we can support, right? We have a list of these drives and products at CODESYS site. You can go in there and see which drives that we've actually certified or worked with. And this is quite valuable to be able to show you where that is. And ultimately, the standard drivers for CIA 402 compatible drives can open. Also, sometimes you see it on EtherCAT COE and SOE. This is very common. This is really, I have actually a lot of steppers and different things here. Personally, I work with, and I use that quite a bit. If you need further drives, it's possible upon request. So if there's something you needed, let us know. We can definitely look at that. Special driver for closed loop, basically axes controlled over speed and values. Now, this is really unique. I put this little picture here, and to be honest with you, I kind of thought, well, should I put that in there? And I thought, yeah, it's great to know. This is kind of referring to doing basically position control and specifically talking a little bit about variable frequency drives. If you have a set velocity, you're able to feed back in with a position control, such as an encoder, and then you can actually control you can control the position of it, right? But keep in mind that that's really going to be based on your system. So you're going to have to know, your loads, the kinematics of it, speed up and down, the weights, and really how good of torque your drive has, or whatever you're using the device. So the beauty is that we have our SoftMotion drive supports unlimited number of virtual axes. So we'll be looking at that. Simple device configuration. For any of you who have not seen this is really nice. You basically say module, 360 degrees. Finite, it's going to be, you're going a length, and you put in software error reactions if you want to have it. In this case, they go to 0 if something happens. This is module, so we're doing 360 degrees. And you put in your dynamic limits of velocity, which is going to be in units per second, acceleration, deacceleration, jerk. You have your velocity ramp type. Do you want a very stiff system? Generally in robotics, you're probably going to use trapezoid. If you don't want something to break and you want a very smooth transaction, probably going to be referred to like a sine wave, right? It's going to be very more S-curved is what they refer to that as. We have quadratic and quadratic smooth. I try to explain that probably in the same concept, right? Quadratic being very jerky, not jerky, but very precise, dynamic, very stiff moves, very fast, where the quadratic smooth is probably not quite as, a little bit more smoother coming into the accelerations and deaccelerations. Identification is really just for you to identify. It's just a number you put in there to identify that specific axis. So application programming, independent motor and control devices, it's easy, it's reusable. So you can kind of go back and forth, you can mix, and you're able to do it. And that's the key thing when you're doing your program independent of the motor, and you can work with doing those two pieces. And they are reusable, right? You can use whatever you used here, you set this up, you can reuse it again in maybe another project or however you formed it. Easy to configure, the Axes General tab and easy commissioning. I covered this. Again, this is a great feature, and I'll show you how it works. And I think this is phenomenal. It really helps a lot of times just get a system up and running. This specific thing talks about SoftMotion abstract and free drive units. The free drive units, I just want to be clear. I put that on here. What that's referring to is inside there we have some drive units, and you can feel free if you have CODESYS at your place to open it up. It really has drive units. We're going to talk about virtual. It has this SM drive position control. And then there's one called drive virtual, but then it's a logical drive underneath. And this is really more for adding a logical drive, some kind of drive unit. The axis of logical drive mirrors the motion of the master axes. And that's really specific to what you're going to do. If you're going to go down that, you'll know that, hey, I need this specific logical drive. And then the second one is MC free encoder. Really, it's just feeding in a secondary encoder. And for instance, I would refer that to possibly like a line shaft, right? If you're going to replace a line shaft on a machine, you probably run maybe something like a free encoder in. So, okay. So getting back to the basically the normal three I want to talk about is the servo drives. This type of architecture is really common, right? This is probably the most common. You have your drive, or you have your PLC, and you're sending your drive, and your drive goes to a specific position, it closes the loop. Or in the stepper motor, for instance, you have it's basically sending the position control impulse and direction, and we're able to look at jitter, and we're able to kind of resonate that out, and you're sending a specific pulse at a certain rate, and it's going to go to a specific position. But then there's the last one, which is frequency converters, VFDs, and this refers to up here, which is the position control, and this is really IO driven. So you're giving some form of a speed, and you're getting back closing the position with a encoder or some sort of feedback device to control the motor's position. And again, be very clear, that's on a kind of a set velocity is what you're running. So, resources for examples and help when you're within CODESYS. I think this is very important to me is doing tech support. There is the CODESYS application example help. Inside there just has a whole bunch of these. If you go to the CODESYS help and you type in CODESYS application help, there'll be all kinds of stuff for motion, and you can see controlling movement axes all the way through to CNC examples, just everything you could really need to see. If you're unable to get to it, there is over here SoftMotion examples that are probably already on your computer that you maybe not have known about. Program files, go into the actual version that you have, CODESYS SoftMotion, examples tutorial. It'll give you a whole bunch of position control, single to, it gives you different camming and everything. There's different examples and they're all documented. Another place to look is CODESYS Forge. Forge, if you're not familiar with it, has a lot of, that's kind of our interactive family out there that's working in all kinds of different, our environment where people can send in requests or fix or questions and we answer them there. There's always the CODESYS help, which is intuitive, right? That's inside the IDE. And then there's also CODESYS support and product information, and you can go there as well and look. So we come kind of to the CODESYS software SoftMotion software. And there's two parts to this I just want to talk about. There's the CODESYS SoftMotion SL, which is drive configuration, cam editor, libraries, drive interfaces, libraries, and so forth. You can see down here. But if you want to get into the CODESYS SoftMotion CNC and Robotics SL, that's a different package. Just be aware of that. You need to have the SoftMotion SL, and then you can get the SoftMotion CNC Robotics SL. So those, you have to have this, the SoftMotion, before you can get the CNC Robotics SL. And again, you can see in here, the libraries that are inside of there is a CNC editor inside the kinematic, it's basically the CNC kinematics library and the robotics libraries. And here's where you really start doing your axes group configurations. So, gotta make sure I'm on the right one here. CODESYS SoftMotion Basic. I just want to take a minute and talk a little bit about CODESYS SoftMotion Basic, and I've had people ask about SoftMotion Lite, CODESYS SoftMotion Lite. Really, what's the difference? The difference is simply, if you're going to do synchronization, you're going to use SoftMotion Basic. If you're going to do one or two, like one axis, and you're going to be doing it over support CIA 402, you're going to want to use SoftMotion Lite. Here, you're just writing to really registers. You can see here the bandwidth is low, the CPU processor is low. You're not really taxing your system. And again, doesn't mean that you can't use one versus, you can't use SoftMotion where you Basic where you do SoftMotion Lite. It's more so you can't use SoftMotion Lite for synchronization and stuff like that. So, okay, now we finally come to the actual demo part. So I will click on that. Do you see the CODESYS ID in front of you at this time?
Not now.
Not now. Okie dokie. You don't see it, you're saying? I'm sorry.
No, not in the moment.
Okay, just a minute. I'm going to step over here. Oops. This. Excuse me just a sec here. I gotta. I'm gonna, if it's okay, I'm gonna stop sharing and then reshare again. I think that's probably the issue, I suspect.
Yes, try.
Okay, let me stop sharing. And then I will I'll share screen again. And then this time I will select this one. There we go. Can you see it? The IDE?
You have to push the button start sharing.
Sorry. How about now? Do you see it now?
Yes.
Okay, thank you. Sorry for the technical difficulties there, folks. All right. So what I have here is just a standard CODESYS IDE, and I'm going to open up and just create basically a new project. I'm going to put in some axes. And what I'll do is I'll just use my runtime that's on here. Today I'll be doing the CODESYS SoftMotion V364, and I'll be going through and doing the ladder logic diagram, because usually that's the most common right now being used. So, and I'll try to watch my time here. So right now I'm building the application, and right now you can see it's building up the app. It's going through. Be there in a minute. I think I got that. Okay. So as it's opening, you'll see that it automatically gave me the ladder logic diagram as my main program. And down here, it gives me a SoftMotion. I can actually add in a device. And inside of here, this is where I was referring to, that you'll see the different ones. You can see the free encoder, the position control. We actually have some stuff in here for Raspberry Pi for pulse and direction. And then we have the virtual axes. Today we'll be concentrating on the virtual axes. Okie dokie. Inside this virtual axes, as I open it up, you'll see the general tab, the commissioning tab, and then the IO mapping, status, and information. Okay. Inside here, I'm going to do a finite, and I'm going to give it a little bit better speed than what I was running. So we'll say 100 units per second. And in my negative and positive, how far I can go, I can activate limits. I have my acceleration, deacceleration, and jerk set. What I'm going to start off with is I'm actually going to go into the commissioning part of this and show you how that works. And moving right along here. So I'm going to show you the commissioning interface tool that I referred to earlier, that I was saying worked very, very well. Okay. As you can tell here that I have 2 green circles going right now. That tells me that it's active and it is running. I do have it in demo mode. Up here, I'm going to click on commissioning, and you'll notice it says this page is only available in the configure mode. So at the very top, I'm going to change it to configuration mode. I'll get a wrench. I'll click on the wrench, and it says here, application configuration mode. All applications on this PLC will be erased. Do you want to continue? And I do, because I'm going to be commissioning. There's nothing on the machine. I want to bump and move the motors. I want to see things happen. Okay, so while it's building, it's getting ready. It's pushing me into the commission mode. It's building the interface at this time. There's the interface. Here I am. So right now you can see that I have 0 position, tells me the axes, and it says right here, power off. So what I'm going to do is I'm going to do a reset, and I'm going to power the system on. Now it's at a standstill state. I can now give it a distance. So I'm going to give it a distance. I'm going to say 100. And I'm going to give it a velocity of 100, acceleration of 100. I'm just kind of going through and punching a number so I can show you it moving. Okay. Oops, I'm going to give jerk 1,000. And now as I start to move, you can tell that I'm actually moving the axes. I can actually see that I've moved. Now, if you did not catch that, when I was holding the button down the whole time, it was moving exactly 100 counts, let's say, or 100 units. If I hit it again, it'll go up to another 100. So I'm at 211.64. If I hold it for a while and let it go, and I change it again, you'll see that I'm just keep incrementing 100 while I'm holding this button. Okay. Now, if I release this button and I just do little jogs, then it's just jogging it. And again, here I can see my parameter that I'm using. Put that in. And it shows me 100, and this 100 here is referring to basically my scaling right here, my dynamic limits. Okay. So I'm going to shut that off. If there's any questions, you can ask me through the Q&A. But yeah, this is the configuration. Again, this is an important screen, I think, to use. It really is. I'm jumping out of the configuration at this point. I'm going to go back to the program. Okay. So here is my general program. I'm going to create a couple rungs in here, put some stuff down through here. I'm going to create another one. Okay. So I'm going to put some blocks out here quick. And I'm going to go here and I'm going to go look for a block. And I'm going to start with the MC power. It's the most logical part to start with, because I'm going to want to be actually doing some form of turning the power on to the drive or to my application. So down inside here, you'll see that we have the administrative configuration block. And if you've never been in here, these are all the different blocks that we have. And we have everything from power, reset, motion, so forth. So I'm going to pick the power block. I'm going to hit enter. I'm going to give it, configure the block. And I'm actually trying to get that block's properties, the name of that block, excuse me. And this is what I want. This is the name of my axes that I currently have. Okay. So there's my SM virtual drive. And I'm just going to give these some tags at this point. Just make it simple. I could put true on some of this, but you know, oops, sorry. We want to make sure that we got it set up. Oops, S3, okay. All right. All right, and then I have the MC power block. This is really turning the drive on. I'm going to grab another block real quick, and I'm going to put on the, I'm going to call it the MC move or move absolute. And I'm going to go up into here. And again, I'm showing you the folders. I was in the administrative block. I'm now going to go to the movement block. And I'm going to do move absolute. Okay. And again, I just copy this axis over. And this is the axis I'll be running. And again, I'm just going to call this one, we'll call it P1 for position 1. So simple enough. It means I'm going to execute it. And I'm going to give this a position. I'm going to actually call this pause. And all right. And the velocity, I'll give it, oops, give it 100. Kind of cruise along here, making this one move kind of fast. Okay. And I'm going to come over to the busy now. Well, the reason I'm getting rid of these is I'm just not putting tags on them today. But obviously, if you were doing an application, you're going to want to put the tags on here and talk a little bit about that and have some way of being able to see your error ID and so forth. So I will now log in. And right now it's logging into the actual controller itself. You can tell at the bottom I've put the code in. And what I like to do at this time is I will start the axes up, move that over, and I'm going to close that out for a minute. And what we're going to do is we're going to turn on the axes. We're going to enable it. We're going to turn on the regulator and this drive start. And then one thing I like to do is I like you to see it's actually moving. That might help. And what I'll do now is I'll actually go into the windows. I'm going to do a split screen so we can actually see the general, and we should be able to see this moving. And not only that, we'd be able to see any sort of seeing the drive is at the standstill mode right here and that there's no errors. I'm now going to give it a position. I'll write that position in. And now I will give it an actual move. And you can tell that I turned it on and the move went right away to 124 and the busy and the active were high and they went low. Okay. So if I did do another move similar to this one, just like this, what would happen is we would actually see it move and then it would stop. And if I had, let's say, this absolute move 0 and I had another one called absolute move 1, what would happen is if I turn this block on and I turned another block on below it, this is on and I interrupted with the second block, this will automatically say command aborted. So I guess I hope this was valuable. I was able to show you a little bit about the actual drive itself and talk a little bit about everything. I guess I'd like to thank you. This will end my presentation at this time. Again, thanks for watching. And